Okay, solving right triangles. So trigonometric functions that we've been using, sine, cosine, and tangent of angles, are used to find missing sides. That's what we've been doing in the last couple of sections. But there's also something called the inverse trig functions, and the geometry book actually fails to mention these, but it's really important, and I think you need to know it. So the inverse trig functions are used to find missing angles. Okay, so I'll show you how that works. So we're going to still use SOHCAHTOA if we've got a right triangle. So looking at this symbol is theta. That's just for an unknown angle. We usually use that symbol. Okay, so hey, we want to be at the acute angle that's marked. That's down here. That's our perspective. And then I'm looking from there. This is the opposite leg and the hypotenuse. So then I'm thinking, what part of SOHCAHTOA? Well, opposite hypotenuse, I'd want to use sine. That's the SO part of SOHCAHTOA, right? So the sine of, where am I? Well, I'm at the theta angle. I don't know the measure of that angle. I don't know if it's angle A, B, or C or whatever. So I'm just going to put sine of theta, okay? Equals opposite over hypotenuse. Opposite is 3. Hypotenuse is 5, okay? So if I asked you for the sine ratio of that angle, it's 3/5. But I'm not asking you for the sine ratio. I'm asking you what is the value of theta. So what is the measure of that angle? Okay. Now here's where an inverse trig function comes in. What an inverse trig function is going to do is allow us to solve for a variable that's inside of a trig function. Okay. So I'm going to use the inverse of sine, and what that's going to do, that's going to switch the position of those two things. Okay. So here's how I'm going to write this. The sine, I'm going to say sine to the negative first, okay? So this part right here just means the inverse of sine. Okay? Sometimes you'll see this written as arc sine. That means the same thing. Okay? And you could write out inverse sine, but this is just to save us some time there, okay? Now those two underlined parts are going to switch positions, okay? So that means I'm going to put the 3/5 right here, and I'm going to put the theta right there, okay? And just to make it clear so it doesn't look like this is negative 13 up there, I'm going to put the contents of that trig function in parentheses there, okay? Now, some people are going to say, sine to the negative first of 3/5. That's not really the same thing. Notice we're not raising a number to the negative first. Okay, so this is just a symbol for the inverse sine. Okay, and also notice we didn't put the -1 right there like you might think you would with a typical exponent. Right? We're doing the inverse sine of 3/5, and now I've got something that I can put into my calculator. So I should say this. So I'm going to put this into my calculator, okay? And my calculator knows that when the opposite and hypotenuse are in a 3/5 ratio, you know, wouldn't matter if that's 6 and 10 or 9 and 15. They would still be in the same ratio, and that this angle is going to remain constant. And our calculator has that angle programmed into it, okay? So here's how I'm going to do that. If I zoom in a little bit, this is the same on almost all calculators. You still probably can't see it, but there's sine, right? Inverse sine is right above that, the superscript above that. Get that stuff off there. So what I'm going to do is hit second and then sine. Okay? Oh, also, I want to make sure that I'm in degrees. You could answer this in radians, but I want to answer in degrees, so hang on. Let me take a step back. I'm going to hit the mode button. And hey, I'm in degrees, so I'm good to go there. Okay, so getting back to this, I'm going to hit second sine, and then I'm going to type in 3/5. Now, some calculators might not allow you to put 3/5 inside, so you might have to figure out what 3 divided by 5 is. It's 0.6, so you could do the inverse sine of 0.6, okay? And then I hit enter, and it's going to give me my answer in degrees. It's this many degrees. I'm going to go to the nearest hundredth, so this would be 36.87 degrees roughly. Okay. So it's really the same kind of thing. You're just setting up a trig function using SOHCAHTOA, but then if you don't know the angle, you're going to have to use the inverse of that trig function. Okay. So let's try another. Okay, so you can pause the video if you like. These are all inverse trig function. Use SOHCAHTOA first to set it up. So here I've got opposite and hypotenuse. That's sine again. I'm at the theta angle. Opposite 7, hypotenuse is 12. And now I want to isolate theta. So I'm going to switch those positions, and then I'd be using inverse sine. Okay, so inverse sine of 7/12 is going to equal theta. Now I've got something to plug into the calculator. Okay. And I know I'm in degrees still. Inverse sine of 7/12. Some calculators you might have to do 7/12 first, then do the inverse sine of it. Just play around with yours, but you should end up with about 35.69. And this is in degrees, so I always want to put the degree symbol, unless I'm going for radians, because if you don't put the degree symbol, it's radians, means something totally different. Okay. All right, so over here, I've got opposite and adjacent. So I'm going to use tangent. Tangent of theta equals 13/5. So I'm going to do the inverse, and we've got an inverse of tangent and an inverse of cosine working the same way. So I'll just use second tangent button on my calculator. Okay. So let's see. Right. So those two things I underlined, switch positions. I also flipped the this around, but you could. Doesn't matter. You can leave it like that, right? And then let's see. Inverse tangent, so second tangent to get that inverse tangent, 13/5 gives me about 68.96. That is in degrees. I'm in degree mode. Okay, and it seems reasonable. If I got a negative angle, I wouldn't like that. Or if I got an angle that was 500, that would seem pretty weird too. So I'm expecting an acute angle, right? You get something else, you might be in the wrong mode. Okay, down here, adjacent leg and hypotenuse. You guessed it, it's going to be cosine, so I gave you one of each here. So cosine of theta would equal 6/20. Now you can reduce that if you want, but it doesn't really matter because we're just going to type it into a calculator anyways. So I'm going to use the inverse cosine of that fraction. So 3/10 is the same as 6/20, right? My calculator doesn't really care. Inverse cosine of 6. I don't know why I have to always tilt it like that. Okay. So 72.54 degrees, roughly. Okay, and that is how to use inverse trig functions. You use them to find unknown angles with SOHCAHTOA. Okay, all right, so next topic is solving a triangle. Okay, so you got to know, what does solving a triangle even mean? So some people, when you see a problem where it says solve this triangle, they'll find the area, and that's incorrect. So solving a triangle means finding all of the missing sides and all of the missing angles. Okay, that's what solving means. So let's do a little recap. Well, how could we find missing sides of a triangle? Our first method we had at our disposal was the Pythagorean theorem. So this is going to work when you have two sides of a right triangle and you need the third one, right? So you can use that in that scenario. Then we had the special right triangle relationships. Okay, so like a 45, 45, 90, even if you don't have two of the sides, you can figure out the other ones by multiplying by the square root of 2. Or you could do the same thing with a 30, 60, 90. Take the short leg times root 3, and that will give you the long leg. Or the short leg times 2 will give you the hypotenuse. And then SOHCAHTOA. If you don't have a special right triangle and you don't know two of the three sides, you can still use SOHCAHTOA if you've got enough information. Okay? To find the measure of angles, we can do two things. We can use the inverse trig functions, which I just covered. So really, that means we're doing SOHCAHTOA again. It's just you'd have to use the inverse of sine, cosine, or tangent. Okay? But there's another method too. Once you know 2 of the 3 angles, you can get the third one because they all add up to 180. So you can use the triangle angle sum theorem, which just means the sum is 180. Okay? All right. So let's solve this triangle. Again, it's not finding the area. Although if this was a multiple choice question that I was writing, one of the options would be whatever the area is. That would be a wrong option. So the correct option, I'm going to say what the measure of all the missing sides are. So I'm just missing side C here, and then I'm going to find the missing angles. So angle A and angle B. By the way, notice angle A is across from side A. Angle B is across from side B. Angle C is across from side C. It always works like that. Also, we use uppercase for angles, lowercase for sides. So that is really helpful on these problems. Okay, so let's think. Well, let's start by finding side C. I can do that because, hey, I can use Pythagorean theorem. Okay, I don't actually have enough for SOHCAHTOA right now. Well, actually, I could use SOHCAHTOA because I got 2 sides. If I was at one of these 2 angles, I could do that. But I'm going to use the Pythagorean theorem. Why not? A squared plus B squared equals C squared. Okay, and just make sure A and B are the sides, which they are here. So 21 squared plus 20 squared equals C squared. 21 squared is 441. 20 squared is 400. 841 equals C squared. Then I'm going to take the square root of both sides. And I only want the principal root, the positive root, because this can't be a negative length of that segment. And if you put this in a calculator, it is a perfect, 841 is a perfect square. So I get an integer answer. But, you might get decimal answers here. This one just happened to be an integer. Okay, so I got that piece. And I always like to add it to the picture because it might help me find some other pieces. And then also helps me realize when I'm done, when I got all the bits. Okay, so I'll call this theta. I could have put my theta down there. It doesn't matter. Okay, so then when I'm looking for this angle, so I'm still going to call it angle A just to make sure it's clear what angle I'm talking about. Now I got all 3 sides, but just in case I made a mistake finding side C, I might as well use the 2 given sides so that if I missed this part, I'll still get this part correct, assuming you know how to do this. So from here, I'm using opposite and adjacent. So I'm going to use tangent. So the tangent of angle A is going to equal 21 over 20. Okay? Now, I can use my inverse trig function to switch those 2. So the inverse tangent of 21 over 20 is going to equal angle A. Now I got something I can put in my calculator. Inverse tangent 21 over 20. That's going to come out to 46.40. So I wouldn't round that to 46.39. It's closer to 46.40, right? Going to the nearest hundredth here. Okay, and this is in degree mode. So that's the measure of this angle. So let's put that in the picture. 46.40 degrees is angle A. Now I'm just missing one bit. And yeah, you could go through with SOHCAHTOA. I could do tangent of B equals 20 over 21. Nothing wrong with that. But I'm just thinking, hey, all 3 of these angles add up to 180. So, and actually a little shortcut, since that's 90 degrees, the other 2 angles must be the other 90 degrees to get to 180. So these 2 angles are going to add up to 90. The 2 acute angles are always going to add up to 90 degrees. Okay, and since I know that angle A is 46.40 degrees, roughly, then I can just do this. And now I can subtract 46.40 degrees from both sides. And then angle B will come out to 43.60. I always like to put in the picture. Oops, I should say approximately that. Now I know I've got all the pieces, right? I got all three angles, all three sides. This triangle is solved. Okay? All right. Let's move on. Now we're going to go to area. So again, a lot of times when I say solve, people find the area. Well, now we're finding the area, not solving. Okay? Finding the area, that doesn't mean I need to find any of the angles here. I could find the angles, but don't need to. Finding the area. So the area formula for triangle, hopefully pretty familiar with that. 1/2 of the base times the height. The base and the height have to be perpendicular. So hey, I could use this as a base and this as a height. Or I could use that as a base, this as a height. Work out the same either way. So 1/2 of 12 is going to be 6. So this is going to be 6 units squared. All right, so that's a little review there. All right, so let's try another. Okay, going to use 1/2 of my base and my height. Uh-oh, I don't have a 90-degree angle here. Okay, so some people will look at this and they'll say, well, that kind of looks like a 90-degree angle. So let's use Pythagorean theorem, and then I can find this side and do 1/2 of 5 times whatever this is. Well, don't assume that's a 90-degree angle just because it looks like one. Maybe it's an 89-degree angle, or maybe it's just a horrible drawing. Okay, so that's not what I want to do. But what I can do, you can pick either the 5 or the 6 as your base. I'm going to use this as my base. Okay, if that's my base, the height that's related to that is right here. Okay, so let's call this the height. I'll put that out here. Okay, now let's think about this. I could actually find that height using this right triangle. Okay, I don't know that some people are going to assume that this is 3, but I don't know if that's cut in half or not. Maybe this is 2 and 4 or whatever, right? So let's forget about the 6 at the bottom for a minute. I can still find the height using this right triangle. So if I'm down here, got opposite and hypotenuse, so I can find it using sine. So I can say the sine of 70 degrees, that's where I am, is going to equal h over 5. Okay? So now I'm going to multiply both sides by 5 to isolate h. Those would cancel right there, right? Okay. All right. So I'm just going to leave that. I could put that in as a decimal, and I will do that in a minute. But my height is going to be 5 sine 70 degrees. I'm just leaving this exact for right now. 5 times the sine of 70 degrees. Okay. So now, using the formula, hey, this is my base, right? This is my height. 1/2 of base times height. Area is going to equal 1/2 of 6 times the sine of, 5 sine 70 degrees. My height was 5 times the sine of 70 degrees. Okay, and now I can start simplifying this. So 1/2 of 6 is 3. Right? So now I've got 3 times 5. This is going to simplify to 15 sine of 70 degrees. And I can type that into my calculator. Make sure you're in degree mode. And there we go, about 14. Oh, we're going to the nearest hundredth. It's not 14.09, right? It would be closer to 14.10 than it would be to 14.09. So this is 14.10, okay? And this is area, so I do want to show, even though I don't know what kind of units these are, I want to show that they're square units. So approximately 14.10 square units. Okay, so that was kind of a lot of work, but I got some good news because there's a nice little shortcut, okay? It's called the SAS triangle area formula. So I still used my basic 1/2 base times height, but it just took me a little while to figure out what the height was. But hey, if you look at the original problem, I've got 2 sides and an included angle, right? Those are given pieces of info. So SAS, 2 sides and an included angle. So this is going to work for any triangle in this format. Okay. So what I can do there, my area, it's still going to be 1/2 base times height, but there's just going to be a little twist. So the base in this last problem was 6. It was just one of those given pieces. Okay, but then when you think about how did I get the height? Well, I got the height, it was my other side times the sine of my angle. So if B was one of my sides, C would be my other side. I mean, it doesn't matter what variable you're using, but this is a lowercase c, okay? And then it's the C of the included angle, so I'll call that included angle, angle A, okay? So this is my formula. So usually we'll just write that 1/2 lowercase b, lowercase c, times the sine of A. This is my SAS area formula. I just derived it. Okay? And these are the sides. And then this is the included angle. Okay? So it's kind of, these problems are actually really quick when you realize, hey, I've got SAS situation here, 2 sides and an included angle. And if you know the formula, then I can just say, all right, area is going to equal 1/2 of the product of my sides here, 6 and 7. There's my sides, and I'm going to take the sine of the included angle, so the sine of 80 degrees. And I'm just going to put that all in my calculator, right? So I'd have 1/2 of 42 here. 1/2 of 42 would be 21. So if I needed to give an exact answer, that's the best I can do. But usually we're going to do a decimal approximation. So 21 times the sine of 80 degrees is about 20.68. Okay, again, I don't know the units, so I'll just say that many square units. Okay, and that is the end of the section.